All right. So the schedule, let me move this thing out of the way. There we go. I just put up some new stuff yesterday. Lecture 4 and example 4 is ready to go for next week. So we'll be transitioning into models that have more than one slope at the same time for a single predictor. That's the topic. So getting to nonlinear types of relationships as well as categorical predictors that have more than two categories. So that is what's on tap. And I've already decided that whatever we don't finish today in lecture 3, I'm going to make a video to finish it tomorrow and give you the link to that because there's not too much that is actionable. It's more sort of a theoretical discussion of what it means to pick the GLM. So we won't lose too much ground, I think, if I can do that. That way we can start lecture 4 next week. As I sent you an email, no homework or formative assessment due next week. You have a week off. Can I get some applause or something for that? Yeah, a whole week off. So homework 3 is not due until the 26th. However, my hope is that at the conclusion of today, you should be able to do all of it. And you can do at least half of it right now. So we should be in good shape. And if not, then I've got the extra cushioning to go over things next week if there's problems. So, all right. Any questions, comments, logistical things before we dive into content? No. Okay. I fixed homework 2. So what had happened is that inside all of the calculations for the points, it was based on 13 points internally, even though it was supposed to be 14. So I discovered that the easiest way to fix it was just to say it's going to be worth 13 points instead of 14. So I went through and corrected that error. So everything is based out of 13, and the extra point will show up in homework 4, which will be the longest one, actually, just to get you ready for that. That one's going to be historically the most fun. Challenging, but in a good way. Just remember, if this was stuff that you could teach yourself in 10 minutes off the internet and have no problem, then this would be a waste of your time, energy, and tuition, right? You signed up for a challenge, and that is what I am here to give you with relish. All right. So what have we been talking about? Tell me what you remember from the last couple classes. To do that, I'll give you a nice pretty background to stare at, something soothing. What do you remember? GLM. Yes. What does GLM stand for? General linear models. Yes. So linear is the idea that it's constant times variable plus constant times variable. General is the idea that the model residuals are supposed to have a normal distribution. So even though the word is general, that has a very specific meaning. We remember slopes and residuals. Yeah, what's a slope? I'll accept a gesture. You don't want to have a definition. Yes. Is this correct? Is this a positive slope? Or is it this way? I have to do it backwards. It's this one. Okay. Yes, so this is a positive slope. This is a negative slope. The idea of describing an association between an X predictor and a Y outcome, yes. And we're going to test whether or not the slopes are significantly different than 0 as a measure of association. Residuals, how far off from the predicted outcome your actual outcome is. So to what degree has the model missed in what the outcome variable is thought to be? So we want the residuals to get smaller and smaller and smaller as we add more predictors to the model. We don't care about the residuals for the individuals per se, we care about their variance. So we're going to be looking at residual variance as a quantity that measures sort of unexplained information. And as we add predictors to the general linear model, we want that quantity of unexplained information, residual variance, to shrink and shrink and shrink and shrink. Yes, we have T. T-test statistic is now T-value. Yes, that's what it says on the output, and that's what it's easier to say. So generally speaking, a shortcut to the language is the name of the test statistic and then the word value after it. So we'll have a T value and an F value We don't say R value for whatever reason. That's not a thing, but we do say P value. Um, empty model is another one. What does empty model mean? Yeah, no predictors. Yes. So the idea that if you don't know anything else about a person, your best guess for what their outcome value is going to be is the outcome's mean. So that's our naive jumping off point from the empty model. And the E sub I residuals in the empty model represent all of the variability there is to be had in that outcome. So it's like the worst possible model you could have, and everything that we would do from that point is an improvement. And what kind of predictors have we talked about so far? I'll give you a two choice, quantitative predictors or categorical predictors. Yeah, continuous or quantitative. The ones where numbers are numbers. That's what we've talked about so far in fitting a slope through. And what we're going to do today is add to that list with binary predictors. We're going to fit a slope that describes the difference between groups that have a 0 value and groups that have a 1 value. And it works exactly the same way. That's a good summary. By the way, what you are currently learning, what we're working on right now when we have quantitative predictors of a quantitative outcome, this is called a simple linear regression. Don't you love it when names are condescending? It's a simple regression. Simple as opposed to a model that has more than one predictor in it, which doesn't have a word for it. That's just a linear regression. It is a simple linear regression if there's only one predictor. But in terms of adding to your list of all of the skills that you now have that go on your CV, things, the models that you know simple linear regression. To the end of today, you will know two sample t-test or independent samples t-test, which is what I call having a categorical predictor with two categories in a general linear model. All right. Any questions before we dive back into making Sas and Stata do our bidding? All right. Then this is page 6 of example 3, demonstrating how to create a new predictor variable that has been centered so that 0 means something and enter it into our model. So education is the predictor that we're working with in this data set, and annual income in thousands of dollars is the outcome variable. So education is the X, income is the Y. And I have chosen a middle value for education centering as 12 years of education. Would it be okay if I had picked 13 instead? Is there anything wrong with that? No. Would it have been okay if I picked 0, if I left it uncentered? Is that wrong? No? Is it weird? Yeah. So that's the distinction. If I had left education uncentered, the model works exactly the same way. The slope is the same. The amount of variability that is predicted by education is the same. The difference lies in the interpretation of the intercept. So our three vocabulary words: intercept, expected outcome when the predictors are 0. So that's why we want to make sure that the predictors being 0 is at a meaningful point. So we have a meaningful intercept. Slope, change in y for a 1 unit change in x. The change in the predictor for a 1 unit change in the outcome for a 1 unit change in the predictor. And the residual, how far off the real data are from the one that's predicted by the model. Can you all see my screen?
Mm-hmm.
Okay, I'm getting notes from some of you. Farhan can't see my screen. Why not? Let me see if I can reshare it. That can fix it. One moment. I lost my controls. Let me see if I put back. Okay, I'm trying again. Is that any better? Okay, I'm sorry,
I'm
Farhan.
still
I don't
seeing
know
a
what's
black
wrong.
screen.
You're seeing the black screen.
Yep.
Okay. Can you see my beach now?
Uh, yeah, I mean, I can see your video, but I can't see your shared content.
Okay, you can't see the share. Kaylin suggests maybe that you leave and come back.
Yeah, okay, I'll try that.
Okay. Let me know otherwise. I'll try to narrate where I'm at, but it's page 6 of example 3, what we're looking at here. Okay, but everybody else can see it. Okay, yeah, I got no explanation for that. So I'm going to center education at 12 years. That means that the first thing that I need to do is make a new variable. So you will get a chance to practice doing this in your homework. Inside SAS, to make a new variable, you always have to tell it which data set you want the new variable to go into. So in SAS, there's this extra part right here that you have to use data and set. Data means make me a new data set. Set means from this particular data set. And so by listing the same name of the data set in both places, you are opening that data set, adding information to it, and saving it as the same name. So to make a new variable, it's the name of the new column that you're creating on the left-hand side of the equals. And on the right-hand side of the equals is the old variable name, the one that currently exists in the data, and then whatever mathematical operation you want to do to it, such as minus 12 and a semicolon, because that is a complete statement. And Farhan says it's working. Hooray! Turn it back off and turn it on again. Doesn't that always fix it? That and like sit in front of someone when you ask for help and it magically works for no reason, even though it didn't work before. Yeah, that always makes it work. I'm glad it's working. Okay. And then for good practice, I'm adding a label here to describe what ed12 means. So as I said last time, my convention in creating new variables is to put the centering constant at the end of the variable as part of the name. So you can adopt whatever convention that you want in making new variables. The shorter the name is, the less typing you'll have to do. So as long as you need it to be to remember what it means, but as short as possible so that you don't have to worry about typos and make your life harder than it needs to be. So that new variable then goes into my proc GLM. So the model line here functionally is like an equation. The word that is to the left of the equal sign is the name of the column that holds your outcome variable. The equal sign then gives you the delineation where the predictors start. So EDUC 12, education 12 is the predictor in my model, and then the slash separates out options for what is to show on the output. And so that will pretty much always be the same. This is asking for confidence intervals for the 95% confidence level, alpha of 0.05. This stuff down here we're going to get to in just a second, but are there any questions about just making a new predictor and putting it into SAS? No. Okay. So let's look at the SAS output and then we'll look at this data output. So the things to pay attention to, this one right here, there's your first stop. So that number in the column labeled mean square and the row labeled error, that is your residual variance. So that is all of the variability in the E residuals across people after controlling for education. So how far off each actual Y is from the regression line created by education. So we're going to need that. And in doing your homework, if you get that number right, then you have the right model, meaning you have the right combination of outcome variable and predictor variable. Now the next thing to pay attention to are my fixed effects, my intercept and my slope. In SAS, the intercept is always listed first. So this 13.99, which rounds up to 14, that is going to be my expected income level for somebody with a high school degree. When education equals 12 is when my predictor equals 0. If you have the wrong estimate for your intercept in the homework portal, that means you have not centered your predictor correctly because it is specific to what 0 means. And so it has to be right with respect to the centering to get the right intercept. So the first column is the estimate itself. What is the value that best fits the data for what that parameter is? Standard error is next. So that's my index of inconsistency. The standard error tells you how far off a sample slope would be on average from the population slope. It's a function of the residual variance in the numerator and the variance of the predictor and sample size in the denominator. So it works just like the standard error of the mean did, but this is the standard error of a slope. If I take, or excuse me, this is standard error of the intercept. I'm on that line. Likewise, for the slope, I've got an estimate and a standard error for that. So each parameter that you estimate, each term that contributes something inside the model has an estimate and it has a standard error. If I take these estimates and divide by their standard errors, that gets me to this t-value column, excuse me. So 11, for instance, that's my t-test statistic, forever forward known as my t-value, for my slope. And that tells me how many standard errors away from the null hypothesis my estimated slope for the sample turned out to be. Do you remember, roughly speaking, what t should be to hit the benchmark of significant or where unexpected starts? 2. Yeah, so 11, definitely more than 2. And here's the p-value that goes with that t. That is the probability of observing a slope as extreme if the null hypothesis of the slope is 0 is true. So we're way out in the tail. It is unlikely that we would get a slope this big if the true slope in the population were 0. And the last two columns then give you the confidence intervals. Okay. With me so far? All right, I'm going to do the state version real quick and then come back up. So I'm skipping ahead just a little bit for the sake of consistency. So state of folks, I'm on page 7. First step is to make a new variable. And because Stata only allows you to have one data set open at a time, at least up through, I think version 16 has changed that, but that's within a separate thing. So that's pretty much the same. You can say that that is true. You don't have to tell it which data set you're working with. It knows. So all you need to do is make the new variable. So the keyword to do that is gen. It stands for generate. The term to the left of the equal sign is the name of the new column that you're making, and the term to the right of the equal sign is the old, and then the mathematical operation such as subtracting 12, and for good documentation, adding a label here as well. And then these two lines right here get you the equivalent to where we were in SAS with procglm. So the command is regress, stands for regression. And the first word after regress is the outcome variable. There's no way you would know that looking at this. It's just the rule. The second word after the outcome variable is where the predictors start. So right now we only have one predictor, and so that's the end of the list. The comma here separates off options. So comma level 95 is saying that we want confidence intervals for the 95% mark. The same thing as alpha 0.05 in SAS terms. We'll get to the rest of this in just a second. And so your output is structured similarly to SAS, but with just a little bit of differences. Your mean square column is just given as MS, and rather than the word error, it's labeled as residual, but those are the same thing. And so it's the same value of 122. That's your residual variance. And the table of fixed effects, the rows are in a different order. So in Stata, the intercept is called the constant, and it's always last. That drives me nuts. I don't know how to fix it, or if it's fixable, but that drives me nuts. And then the slope that you added is listed first. And then rather than having the first column be labeled estimate, it's labeled coefficient, but it's the same thing. Standard error is next, and the estimate divided by the standard error gets you your t. And then p is 0 to 3 decimal places. And then here's the confidence interval that goes with it. All right. Stata folks, any questions on that?
I have a question about generating new variables.
Mhm.
Can you do like all sorts of mathematical like calculations
Yes.
with that? Okay.
Yes. Some of them require, rather than gen, a command that isegen, just stick an E in the front. But there's a whole bunch of built-in functions in terms of like you can take the average, you can take the sum, you can take the log. Like just ask the Google for it and you'll find out whatever it is. But yeah,
Great, thank you.
sure. Other questions? Okay. So here is some outputs, some pictures that I got out of the ProcGLM process. On the right here, this is the regression line. So I want to point out something in this picture. And in order to make sense of that, I've got a prop. I've got a prop for today. This is a telescoping stick. This used to be my teaching pointing stick back when I did this in person. And I would like hit the board and like, go poke people who were asleep and stuff like that. It's very fun to have a stick. I highly recommend it. I started with the stick back when I first started teaching, and I looked very young, and I thought, well, this will help me feel more professorial. I don't have that problem anymore, but I still like the stick. So the picture here on the right is showing the regression line. And around the line, do you see the blue shading? Do you see how it's narrowest sort of in the middle and the blue shading gets a little bit wider as you move out? What that is conveying is the precision of the predicted values along that regression line. So the standard error for what the model predicts each person to have on the basis of education. And the reason that that line has shading that's smallest in the middle and widens as you go out, it's easiest to think about if you can wiggle the slope, right? The word fulcrum is coming to mind. Is that word appropriate here? The idea that if you wiggle the slope, if you change the slope, the predicted values that are in the middle stay pretty much the same, but a change in the slope has a bigger impact on where you are at the extremes. So it's harder to pin down the extremes with respect to what the slope predicts than the middle. So if I were to generate predicted outcomes based on your education level, I would expect there to be more precision in those predicted outcomes the middler I am on the distribution. Specifically, at the mean of education is where the standard error for the predicted outcome is going to be the smallest, and it grows as you move outward. And in the slides, let me go back to this for just one second. I have this picture and this idea, and I have the actual formula somewhere. Here it is. It's on slide 20. So in case you want to see the math behind it that the program is using to compute predicted outcome values for each person and their standard errors, you can find the standard error with this formula, and it's a function of where you are on X. The further you are from the mean of the predictor, the wider the error is, the less confidence you have in what the regression line would predict for each individual person. The picture on the left, this is a picture that describes the variability across people of the E residuals. So this is what's left. So for each person over here on this line, if I were to calculate for each bubble how far off their real outcome is from the one that's predicted by the shaded line, Then the picture on the left shows the distribution of those offnesses, of those residuals, of those discrepancies. And the thing about the general linear model, it's those discrepancies, those residuals, that is supposed to have a normal distribution. So this is a point that we'll talk about more later, but I wanted to show you just as a point of contrast what the data looked like to begin with. Okay, so here's income. That is my outcome variable just all by itself. That's what it looks like. It's not normal. It's positively skewed. But income that is left over after being predicted by education, the distribution of the residuals income, that's what's supposed to be normal in order for to believe the standard errors for these parameters and their associated p-values. And so we can see from the blue line, that's what it would look like if the distribution were normal, and the red line is tracing what it actually looks like. They're not perfect, but it's not bad. Like this is like ish, right? And so this is why I assigned an article about this. This is a really common misperception in using these models is that there are well-known textbooks that have whole chapters on data cleaning and transformations to make your variables look normal. And they advise you to do all of this stuff before you start modeling your data to make sure that your variables are as normal as possible. You don't want to do that. The outcomes don't have to be normal. It's the residuals that are supposed to be. And you don't know what the residuals look like until you fit a model. So it's hard to say whether or not like this is normal enough. In my other classes, I go into options that you have. If it's not normal enough, you may have to change your model or you may have to change the way that you estimate it to adjust for the fact that it's not normal. But it's looking at these sorts of pictures of residuals that allows you to get some indication as to whether the model is appropriate for the data. Not whether what the data look like to begin with, but the residuals. And we'll look at more pictures of these in the coming examples as well. Okay, questions? Let me pause. I've had enough caffeine today, so we're going with the Diet 7-Up for the afternoon. All right. So can I teach you some shit that I wish I had learned a long, long time before I did that makes your life easier? So I'm a big believer in making software do your bidding. I didn't recognize until far too late just how far you could push that idea. I want to give you the ability to ask the software to compute linear combinations of your model parameters. Basically, to ask it to estimate all of the quantities that are implied by the model that aren't directly given by the model. So as your first example of this, the idea of predicted values. So I'm back on page 6 for SAS, and we'll do Stata in the same way in just a second. So here's my model. Make this a little bigger for you guys. My model says that the income for any individual is a function of a fixed intercept and a fixed slope for education. So given any value of education, I should be able to come up with what the model says your predicted outcome should be. If you want to make pictures that show the results, showing pictures of slopes is a good way to convey the results, particularly when you get models that have lots of predictors or that have nonlinear effects of predictors. So what I am asking SAS to do with these commands right here, so I copied from up above so that we could focus on those directly. These estimate statements are like little calculators. They allow you to make SAS do math using the estimated parameters to predict other things. So if I take my model here and say, okay, well, what would my model have to say about somebody with an 8th grade education? What is their annual salary predicted to be according to my model? That's a question I might want to answer. Well, notation, y hat. Do you remember y hat? It's what the model says your outcome should be. So note that in each of these lines, there's no E anymore, because what I'm doing is generating model predictions based on just what your level of education is, not for particular people in the samples, but just given education. So anybody that has an 8th grade education has the same predicted salary. Well, based on the results that I just got, I learned that the intercept was 14, and I learned that the slope of education is 1.8 and some change. So I could get my calculator out, or I could get Excel out, and I could generate a predicted outcome for somebody with 8th grade education. Now note, it's not 8 that goes in here. It's -4. This is really easy to screw up, but you have to remember that the variable that's in the model is centered. So 12 is now 0. So if I want 8th grade education, I need to enter a -4. And if I put this information in my calculator, it turns out that somebody with an 8th grade education, according to my model, is predicted to make $6,000. Somebody with, say, 16 years of education is predicted to make, hang on, this should not be 4. This should be 0. Typo. These are all off by 4 for reasons that I don't know. I will fix this and repost the new one, but just to make sure that I'm looking at the right math in front of me. There we go. Somebody with 12 years of education has a predicted value of 14. We knew that already because that's what the intercept told me. So that one's just sort of for demonstration purposes. For 16 years of education, I would put in a 4 and I'd get a prediction of 21, and so on. So the model tells me what the outcome variable is supposed to be given my predictor. These statements ask for that same information without me having to know what the answers are for the parameter estimates. So in this statement, estimate is the command. The stuff in purple is a label that you write. It's going to show up on the output. It is your trail of breadcrumbs to remember what you are asking it to do. So I'm saying this is predicted income for someone with 8 years. The words in these lines refer to the estimated parameters. So the word intercept is a placeholder for whatever the fixed intercept estimate is going to be from the data. So it knows internally that when I say intercept, it means go get that number. Likewise, when I list the name of the predictor, I'm referring to its estimated slope. Go get that number. The values in this aqua color refer to a multiplier for what value goes in the equation. So beta 0 as the intercept doesn't get multiplied by anything. So I just need one of those. Beta 1 has to get multiplied by whatever x is, whatever value of education my prediction is for. So for instance, I plug in a -4, that's what will go in parentheses here. So these 4 lines of code are doing the exact same thing as this without me having to type in what the parameter estimates actually are. It's doing it internally. And so then here's the result. We get this nice little table down here that has those estimates that I calculated by hand, but more importantly and more usefully, it also gives you a standard error for them. And that's not something you can calculate as easily by hand. So estimate statements in general are used to create linear combinations of the fixed effects, such as when generating a predicted outcome for somebody who is not the reference point for the model. Okay. Questions on that, thoughts on those? There are commands, by the way, that you can use to generate predicted outcomes for everybody in your sample. Each of the programs will do that with just one more option. So if your goal is to generate predictions for real cases based on the model, that would be a more straightforward way to do it. The idea behind this is just to give you an introduction to what these commands do, because this is how you would generate predicted values to make plots with, to show the implications of your results. Typically, you make plots of prototypical individuals that would have representative high and low values on your predictors to show what the model says about them.
Lisa,
Yes.
can you please explain what the intercept one means in the estimate code again?
So the intercept part is a placeholder for what beta 0 is going to be.
Yep.
And the 1 is just like this.
Oh, okay.
We just need one of them in the equation,
Yeah.
as
Okay.
opposed to needing 4 of them to multiply the slope.
Okay, got it.
If I were to teach you the same information using matrix algebra, in order to make the matrix math work, you have a column of 1s that multiplies the coefficient for the intercept. See, I could make this a lot worse. We don't like matrices, do we? Not yet, anyway. Eventually you may, but not today. Okay, so this idea is actually more transparent in Stata, the way they do it. The analog to this process in Stata is a statement that's known as lincom. That stands for linear combination. And the only difference, actually there's a few differences, but in terms of the labeling, rather than typing out the word intercept, it's that underscore const thing, because that's what Stata calls the intercept. It stands for the constant. And you make the multiplication and the addition that corresponds to the equation explicit. So the constant is multiplied by 1 just to make it consistent with the idea behind the Sas code. And then each of the slopes is multiplied by the predictor value for whom you want the predicted outcome to be. And so the pluses there look a lot more like the actual equation. Where did it go? Right here. And then, unfortunately, the way Stata provides that same information is less efficient. It does so in little separate tables. So rather than having one table that lists all the things you asked for, it spits it out in separate tables. And there's no way directly to put labels onto the lincoms in Stata, and so that's why you'll see these right here. These are actually comments. And so I've added those so that when you get the output back, you can see what the term referred to that you asked for. Okay, how we doing? Yes, you'll get a chance to practice this. You knew that was coming, right? Yeah, it's not so bad. It'll all be red and green boxes, so you can try it as many times as it takes until you get it right. All right. And then, last but not least, so the idea of these slopes, for instance, my slope of education is 1.82. The only way that I know how to interpret that number is in the context of the units that describe the X predictor and the Y outcome. So this is the change in $1,000 per year of education. That's what the 1.82 refers to. If I had measured this in terms of any other units, the slope would have to adjust to describe the units themselves. So several of you wrote about this in your quiz points, like if the scale of X is bigger than Y, then the slope has to absorb that scaling difference, and the intercept absorbs the differences in the means. So I have a slope of 1.82. I know that that's a positive slope, right? I know that that means that as education goes up, income is predicted to go up. And I also know, based on my p-value here, that that slope is significantly different than 0. So it's unlikely that that slope came from a distribution where the slope is actually 0 in the population. But what I don't have here is an effect size. I don't have a standardized way of saying, but how strong is this relationship? Wouldn't it be nice if I had something that looked more like a correlation? Because I know what to do with a correlation, right? I know what those numbers mean. I only know what 1.82 means in the context of these particular two variables. So in general linear models, we can also ask for, in a separate command, what's known as a standardized solution, where we strip the units off of the variables, make them all so that they have mean 0 and standard deviation of 1. So they're all z-scores. And then re-estimate the model. And then the slope is a correlation. If there's only one slope in the model, then the slope is the same as the Pearson correlation. So do you remember like two classes ago when I told you that I was going to reteach you Pearson correlation, but we were going to put it in a model? We're circling back to that now. So to get an effect size for my slope, in SAS, this requires a slightly different procedure known as proc-reg, stands for regression. It looks very much the same, except that there's an option that's available within proc-reg that is not available in proc-GLM. STB means standardized B slopes, standardized estimates. And so here is the same table that was shown from GLM with respect to the estimates, their standard errors, their t-values, and their p-values, with one extra column at the end. The last column here that says standardized estimate, that is what's known as a standardized intercept and slope. The standardized intercept will always be 0. Always, always, always. So there's a few easy homework questions for you. And the standardized slope in this instance is a correlation of 0.38. So now I have a better sense in more absolute terms of how strong is the association between education and income. It corresponds to a correlation of about 0.4. So positive, a healthy relationship, but certainly not like lockstep perfect association, which would be 1. And in Stata, you just need to add the option beta to the same regress command. And that gives you the last column over here, which is your standardized slope. So when all is said and done, a simple linear regression where you have one quantitative predictor of one quantitative outcome, and you fit a linear slope for that quantitative predictor, that is the same damn thing as a Pearson correlation. That's what it is. Now, why would I go to such trouble to reteach you Pearson correlation? I can think of 3 reasons. Well, what if there's a nonlinear relationship? And it turns out for education, that is definitely going to be the case, and we'll explore that in the next unit. Pearson correlation can't capture nonlinear relationships, but models can. If we have questions about, well, why is it that education is related to income? Is it still related after we control for X, Y, Z other things? Can't answer that with Pearson correlation easily either. So that needs a model. And the other reason is that if we want to look at categorical predictors, like nominal variables, like favorite TV show, for instance, then we need a model. So I do have a reason, even though this boils down to the same thing as a Pearson correlation, because this is a framework that allows you to answer a lot more questions. such as categorical predictors. So we can do one for binary in the next set here. So questions before I dive into binary. So it turns out there's nothing new here. It's exactly the same. It's just a little bit weird to think about a slope for a binary variable that's two different categories. But the rules are the same. We have to have the predictor have a meaningful 0 point. So that means taking one of the categorical levels and calling it the 0, and the other one is going to be a 1. So if you're starting off, say, with a variable like in this data set, marital status is coded so that 1 is unmarried and 2 is married. If I left it as is, the intercept would refer to a category score of 0, which is not a thing. So we want to fix it so that rather than having the categories be 1 and 2, they correspond to 0 and 1. In that case, I could just subtract 1 from each and that would do it, but a more general way of doing that is to take it and recode it. So I wanted to show you what that would look like. So first in Sas, again, all data transformations have to happen within that data set combination. So copy that as your first thing. I'm going to first create a new variable for the predictor that's empty. So it's blank, a new column that is called Mary01, set to blank for everybody. And then if the old variable is 1, the new variable is 0. And if the old variable is 2, the new variable is 1. And then I have a label. So now that new variable that I've called Mary01 goes into the model. So I've taken out education for the time being. I have replaced it with marital status to find out whether the people in my sample who are married make more or less money than the people in my sample who are unmarried. That's my question. It might be a stupid question, but it's my question. So my estimate statements, in this case, there's only 2 that are possible. In this variable, you're either married or not. So there's only 2 possible predicted outcomes that the model has to give us. One of them is already given directly as beta 0. So the intercept is always the predicted outcome when your predictor variables are 0. In this case, that corresponds to somebody who is not married. That's what 0 means on my new predictor, not married. So I didn't technically need to write that one, but I did so for pedagogical reasons. This one is the one that I did need to write because the model tells us indirectly what the predicted income would be for somebody who is married, has a score of 1. I have to add the intercept to the slope. So this equation right here, starting with the intercept and then adding the slope times 1 to get to what the model says y is going to be for somebody who's married. So here's my residual variance. Here's my parameter estimates from the model. So in this case, my intercept was estimated at 14.45. So intercept always predicted y when x is 0. So what that means here is that this is the predicted salary for somebody who is unmarried. The slope, 6.22. Now that's kind of weird to think about that as a slope. But it's still a slope even though it's only moving between a value of 0 and a value of 1. So as we go from an unmarried person to a married person, their income is expected to be $6,000 higher, 6,200 and some odd change. So for binary predictors like this one, even though technically this is still a slope, it's probably easier for you to think of it as a mean difference. So what the model is telling us is what the mean income is for an unmarried person as the intercept, what the mean difference is for a married person relative to unmarried. Homework question. Relative to matters. So who is the you are here sign, right? Unmarried people. So that is what the intercept is. For the group coded 1, they are higher by 6.22. So if the 0 group is the intercept, the slope tells you moving from the 0 group to the 1 group, what happens to y? In this case, it goes up by 6.22. Can you guess what would happen if the 1 group made less money? If the 1 group made less money than the 0 group, what kind of slope would I have? Yeah, right. Hang on. I can't do it now. Down. I'll just make a negative sign for down. It would go down. Yeah. So if you have a negative slope, that means relative to the 0 group, the 1 group is lower. If you have a positive slope, is relative to the 0 group, the 1 group is higher. So if I start with an intercept of 14 for the 0 group, and to get to the 1 group, I've got to go up by 6. Then I put those together, 14 plus 6 works out to be 20-ish. That's what the model predicted mean is for the 1 group as the linear combination. And so that's what my estimate statement is going to give me as the extra piece of information, the mean for the 1 group that is implied by the model, but not directly given by the model. Okay. And you'll get a chance to practice this as well. How are we doing?
I have a question, Lisa.
Please.
I don't know if it's an important question, but when you make the married versus unmarried, like when you recenter it from 1 and 2 to 0 to 1, is that because when you collected the data, that's how you had it? Like you said 1 equals married and 2 is unmarried, so then you're recentering it because that's the way you collected the data?
Yes.
Or so if you, when you're collecting the data, if you had said 0 is married and 1 is unmarried, then would that eliminate that need to recenter it?
Yes.
Okay.
That is a great question because that's how it's going to be in your homework. You're going to look at age group, which has already been 0-1 coded, so that you don't have to go through the extra step of coding, changing it from 1-2 to 0-1.
Okay. Right. So it's a collection thing. Okay, thank you.
Yes, and in a lot of data sets that collect binary information, you will see them store it that way to begin with, that one of the groups is the 0 and one of the groups is the 1. And that this is why. So this, by the way, what we just did, this is called an independent samples or 2-sample t-test. That's like one of the dumber names because t shows up in like 8,000 things. So I don't know why they claim that's the t-test because t is all over the place, but that is what is conventionally called. So the combination of a binary predictor variable of a quantitative outcome is known as a independent samples or a 2-sample t-test. But it's all under the umbrella of the general linear model. Okay, so effect size. Same problem as before. I've got a difference of about $6,200. Is that a lot? Depends on who you're asking, right? I know that it's a positive difference, so I know that the 1 group makes more than the 0 group. And I know based on this p-value that that difference is significantly different than 0. It is unlikely to find a slope of $6,200 if the true population slope is 0. I know that, but like, is that a lot of money? I need an effect size. But in the same way that a slope is sort of weird if you think about it as the difference between 2 levels of a variable, a correlation with a binary variable is also sort of weird. You guys just finished homework 2, right? There were a few questions about a correlation with the binary variable, and it was weird, right? There's nothing wrong with it, but it's a little weird to think about. So instead of an effect size in a correlation metric, I want to introduce you to another family of effect sizes, which is in a metric of a standardized mean difference. So this one in particular is known as Cohen's d. Got slides about this. Here's the formula. You can take your t-test statistic for your mean difference slope and reverse engineer a d effect size out of it. And the metric of d starts at 0, meaning there's no difference between the 2 groups, and it can go into negative or positive infinity. So it's not standardized in the way that R is bounded, but it does tell you how many standard deviations apart your groups are. So for instance, a slope of $6,200, given the standard deviations of these variables, corresponds to a d effect size of about 0.5. So my 2 groups are about a half a standard deviation apart. So I can make a little data set that has the math in it, and then that's where I got that number from. I'm going to show you how to make Sas do math to compute effect sizes in the next example. Stata will do the same thing. So here's the corresponding Stata code for this example. So the initial step in Stata to create a dummy coded predictor, as it's called, that 0-1 coding, gen a new column and set it equal to missing. That's what dot means. And then replace where the order is backwards to what it says in Sas, but it's exactly the same idea. So if the old variable was 1, then replace the variable that I just made with a value of 0. If the old variable was 2, replace the value of the variable I just made with 1. And note equal equal, that's not a typo. So it's single equal in the first part and double equal in the second part because they mean different things. Single equal is an assignment, like make this 0. Double equal is an evaluation of does this equal something. It's like satisfying a condition. So if the old variable is equal to 1, make the new variable 0, is how I would translate that. And then the new variable goes into the regress. Here's my linear combinations that give me the model implied group mean for the group coded 1. Those are the, here's the 0 group, here's the 1 group, and the Cohen D. You can have turn Stata into a calculator by typing display and then entering in whatever formula you want it to compute, and it will spit that number back at you. So for categorical predictors in these models, where the slopes represent differences between groups and their means, D effect sizes are going to be more intuitive for people to understand because D is a standardized mean difference. It's how far apart the groups are in a standard deviation metric, whereas slopes that refer to quantitative predictors, where you're talking about a 1-unit change as you move up the predictor, slopes phrased in a correlation metric will be more interpretable in that case. Okay, how are we doing? That's honesty. I know it sounds like a rhetorical question, but it's actually my way of saying, please ask questions at this point if you feel you would like to. Or ask me to repeat things. I'm happy to do that. So here's some words for you. So this is what I would write to describe each of these sets of analyses. So describing the regression of education and income. And then the second part is describing the effect of marital status as the predictor in income. And I wrote it 2 different ways. So the first way is if I were talking about it in a regression point of view. And the second way is if I were talking about it in a 2-sample t-test point of view. For whatever reason, different things are emphasized from each of these perspectives. So I wanted to give you a template to follow that would look like whichever one you're following, that is typically done in your field. In regression, people tend to emphasize the estimates and their standard errors. And in means comparisons, they usually just give the test statistic that is the comparison and then the means. So for instance, I have the t-value here and I have the mean for each group, but there's no point at which I said what the mean difference is. That's typically how you would write it, whereas the mean difference is given front and center when I think about it as a regression. These differences are cosmetic. Okay. Make sure I didn't skip anything in that section. Okay. A few minutes left. Yeah, we're actually almost done. Holy crap. We could finish this for reals. Can you hang in there for like 7 more minutes? Can we do that so then we can call it a weekend? Okay. What choosing the GLM means. So the GLM, general linear models, in order for you to trust the results, certain things are supposed to be true. If these things are not true, you need a different technique. It doesn't mean that there's something wrong with your data or that you can't answer your question. It just means that this isn't the right approach. But everything that I'm teaching you, we would build on to do something else instead. So this is like a core set of ideas that show up throughout statistics and throughout all the models. So here's the point that I was trying to make a little while ago. I should have just went with my slides instead of skipping around the Word document. The distribution on the left, that's what income looks like all by itself, or marginally. The distribution on the right is what's left of income after controlling for education. It's the distribution of the residuals. Said differently, the distribution of income on the left is the residuals from the empty model. Because the residuals in the empty model represent all of the variability in the outcome that there is to be had. On the right, it's the residuals after a predictor. It's the right picture that's supposed to be normal in these models. If not, the standard errors are not going to be correct, which means the p-values are not going to be correct. So it's not the slope and intercept estimates per se that we would worry about, it's their significance tests that are dependent on these things. So what if that's not possible? What if you have an outcome variable that's never going to be normal? Like you're trying to predict whether or not somebody graduates college. Is that ever going to have a normal distribution? No, a binary variable is never going to have a normal distribution. There's a lot of constructs that people are interested in that are never going to have a normal distribution. That's okay. If that is the case, come back to my generalized linear models class. No, it sounds a lot the same, right? But there's a special little end here, the ised. You know what ised means? It means not normal. Something else besides normal. Normal is a special case of a more general family of models. So there are other types of distributions besides normal, and one of them might be a better fit if your data don't have normal residuals. Also, independence. All of this is predicated on the idea that the E residuals are independent across persons. So when might that be broken? Educational data. Like if you're surveying children from multiple classrooms, does that ever happen? Yeah, so let's say you have data about children from multiple classrooms and teachers from the same school, but there's multiple teachers. Well, you might be able to assume that teachers are independent, that you may have put into the model all the reasons why one teacher would be more related to another teacher. But even after controlling for that, the kids in the same classroom are probably more alike, to some extent at least, than kids from different classes. That's the definition of dependent residuals. So these models don't work for that. So if you want to learn how to analyze data where people are grouped together in some way like that, like children from different classrooms, then that's another set of classes that I offer, which is known as multi-level modeling or mixed effects modeling. The idea of those is that we would have two different kinds of E's. Those models would have an E for the teachers specifically and an E for the students specifically. And that helps build in covariance or relationships among the E's that come from students who belong in the same class. So put a pin in that if you are going to want to analyze data like that. Same thing with data that were multiple observations from the same person. The last piece here is the idea of different amounts of variability across the levels of your predictors. So this is a $6 word, homoscedasticity. I couldn't make this shit up if I tried. Homoscedasticity is the third assumption that we're making. So the E residuals are supposed to be normal, they're supposed to be independent, and they are supposed to be homoscedastic. And the opposite of homoscedasticity is heteroscedasticity, otherwise known as constant variance. Let's just go with that. So the idea is that the E residuals, as you move along the regression line, should all be normal at all the parts of the line, and they should have constant variance. Said more simply, I love this picture that I stole from the internet. The picture on the left here with the dots are equally scattered around the line. That's good. That's constant variance. That's what we want to have. And then cleverly labeled on the right, not good. This is a fan shape. What this implies is that the way that the model works gets worse in people who have higher values of the predictor. There's more uncertainty as you move out. They're more different from each other. So that's not necessarily like you did something wrong, but you need to build something into the model that accounts for that. And so those models require leaving the GLM as well, to allow variances to change as a function of the predictor in addition to the mean. They're known as heterogeneous variance models. And I don't have those in any particular class, but that idea gets scattered across some of the other classes as well. So in the data that we looked like, we definitely see evidence for non-constant variance. So here's the fit for education. And it looks like as a function of education, the residuals grow in variability. There's more variability in income amongst people with high education than low. We don't see that as much in looking at the relationship between income and marital status, though. Those groups appear relatively homogeneous. So ideally, we would want to change the model to allow the residual variability itself to adapt along this x-axis. That would require leaving the GLM. All right, so there's your summary. Hooray, we made it. Yay, and here's your foreshadowing. What's coming next? So models allow us to answer more complicated questions about more kinds of variables simultaneously, as well as to examine the potential for interactions, moderations. Whether or not the effect of a variable depends on who you are. Does more education help everybody, or does it help men more than women? Right? It depends, right? That's moderation. That's what I hope we're going to get to by the end of the semester. All right. Questions or comments? Then that is it for lecture 3 and example 3. Hooray, we made it. Starting a new topic then next week. Let me know if you need any help with your homework or if I can help you in any other way, okay? All right. Have a good weekend. Stay safe and stay sane.